In the first lab, we were asked to observe a real-life example of an object moving with constant velocity. In an attempt to demonstrate constant velocity, I decided to roll a ping pong ball from left to right along a table. The motion of the ball was analyzed using the program Tracker and then computationally modeled using the program VIDLE. The experiment data in the computational model were then compared to show that there was no net force on the system and the velocity was constant. Newton's first law and Newton's second law are both essential to understanding constant velocity. Newton's first law states that an object that is in motion stays in motion unless acted upon by an external force, and the same goes for an object at rest. The net force, or the external force that could be acting on the object, is defined as the total of the pushes and pulls on a system. In this case, the ping pong ball is the system and everything else is the surroundings. Thus, in order for an object to be moving with constant velocity, there must be a net force of zero on the system. Newton's second law, or the momentum principle, states that the acceleration of an object is dependent upon two variables, the net force acting on the object and the mass of the object. Or, in other words, the net force is equal to mass times acceleration. Acceleration can be defined as the change in velocity over the change in time. So this brings us to the equation final velocity is equal to initial velocity plus F net over mass times delta t. Thus, in the case of constant velocity, there must be zero acceleration, and in order to get zero acceleration and have the final velocity equal the initial velocity, the net force must be zero. So in my experiment, I used a ping pong ball with a mass of 0.0027 kilograms and rolled it in the positive x direction to the right. So using the data points from Tracker, you can plot the position versus time graph, and the graph was fairly linear, as shown here, which means that it's nearly a constant velocity. The slope of the graph is positive because I chose the positive x direction to be to the right, and I rolled the ball from left to right. The data from Tracker is also very useful because it shows the initial time and position as well as the final time and position. In this case, the time of last observation was 0.733 seconds, with a position of 0.171 meters in the x direction and negative 0.003 meters in the y direction. As you can see from the final position, the ball drifted down in the negative y direction. The movement along the y-axis may have tampered the data I collected for the velocity in the x direction, so that'll be something I'll consider later when I talk about errors. Also, my coordinate axis was slightly rotated to the left in order to line up the motion of the ball with the x-axis. Measurements were calibrated to the ping pong ball, which was measured with a diameter of 0.04 meters. So taking the data I collected from Tracker, I changed important parts of the generic code that was given to us to model the experiment. I inserted the mass of the ball, 0.0027 kilograms, and the position, initial position using Tracker, as well as the initial velocity, which I computed by using the formula change of position over change of time. I also adjusted the delta t to fit the data because it was 100 times smaller than the total amount of time of the observation. Also, this while loop right here iterates until the end of observation, which is 0.733 seconds. And I also was able to change to make sure that the net force was zero, as well as changing the equations in order to get the correct velocity and position after an amount of time. With this data entered into the code, you can run it in order to get this. When you compare the graphs of the computational model and the observed data, the graphs follow the same path at first, but after 0.2 seconds, the model begins to underpredict the position of the ball. I attribute this to multiple factors. First, as you can see in the video, the camera moves from left to right, kind of following the ball. As you can see, the edge of the table comes into the picture when it wasn't there at first. This causes the data collected from Tracker to be slightly incorrect. Also, the motion of the ball in the negative y direction skews the data. In order to fix these mistakes, I should have set the camera down on a table so that the shaking of my hands would not cause the data to be altered. But for the most part, both graphs are linear and very similar in slope, which shows that the velocity was constant. Now for the what if section. If the axes were flipped, then the ball would have traveled in the negative x direction, as originally this was the positive x direction, But if this was the negative x direction, then it would have traveled in the negative direction, and the slope of the position versus time graph would have started up at the top left and gone down to the bottom right. Also, the sign of the velocity and the final position would change from positive to negative. Now, for the what does it mean section, it is not possible to say how many pushes and pulls were added together because we cannot measure the many forces that acted on the ball. What we do know is that the total of the forces added together must be zero in order for the motion of the ball to be in a constant velocity. There could be any number of forces in either direction, such as friction or blowing air, but as long as they cancel each other out, the net force will be zero and the velocity will be constant.